In this video, we'll discuss some methods for making hyperparameter optimization faster. This is very important in the context of deep learning, since deep neural nets often take a long time to train. For example, if your neural net trains for a day, then Blackbox optimization would easily take on the order of a few months. And we of course need to have more efficient methods than that. So let's dive right in. Beyond Blackbox optimization methods for hyperparameter optimization. Here, we will discuss three different speedup techniques for Blackbox hyperparameter optimization, namely meta-learning across datasets, extrapolation of learning curves, and multi-fidelity optimization. Now, for the first two, I only have one slide each because they're interesting, but also somewhat beyond the scope of the course. Multi-fidelity optimization, on the other hand, is what I'm going to focus on because it is what currently provides the most effective hyperparameter optimization methods in practice. And one thing I would really like you to take away from this week is how to use these multi-fidelity optimization methods. So the first speedup technique is meta-learning across datasets. Now, meta-learning is the field of study that tackles learning about learning methods. This can take different ways, shapes, and forms. And for example, you can learn and optimize about the performance of learning methods based on data. So you use data in order to learn about the performance of learning methods and optimize their performance. So if you've run Adam often enough, for example, you kind of know what types of learning rates are useful for Adam. And this sort of knowledge that humans build up, you can also think of building up a probabilistic model based on that data. And then you can actually come up with the right hyperparameter settings very quickly for a new data set. So that's one type of meta-learning. Another type of meta-learning is to actually generate entirely new learning methods from scratch. So that's super exciting, but it's not actually that relevant for hyperparameter optimization here. And the third type of meta-learning is to learn to transfer knowledge across tasks and domains. So that's also a really interesting field of study, but also not that important for hyperparameter optimization. That's more interesting for pre-training. So for learning initial weights of our neural networks across different tasks that we can then fine-tune on a new data set. In terms of meta-learning for hyperparameter optimization, there's actually quite a lot of work dating back all the way to 2013. Most of these methods actually learn a single model across data sets. So that means they integrate performance data, such as how well did each of my different hyperparameter settings perform on each of my different data sets in the past. And then, given a new data set, they can quickly transfer from the information learned from these previous data sets to the new data set. A simpler approach is to learn to initialize the hyperparameters to values that worked well on previous data sets. So this doesn't actually learn a single model across data sets, but it merely learns to check which hyperparameter settings worked well in the past on similar data sets, and then on my current data set, actually initialize with those hyperparameters that are likely to work well for data sets like this new one. And this simpler approach actually has the advantage that it works very well for high-dimensional hyperparameter spaces where the model-based approach might not actually work as well. We, for example, used this in order to build AutoSKLearn, which had a design space of over 100 different hyperparameters that chose the algorithm to use out of scikit-learn and its hyperparameter settings. And basically, for a new data set, we look at from a set of previous data sets what are similar data sets and what hyperparameter settings worked well for those, and those are the ones that we initialize with. And this is already an approach that works very well. And if you use this type of meta-learning, then you can easily reduce the time for hyperparameter optimization from maybe 100 function evaluations to 2 or 3. So if you have good metadata available, then meta-learning is definitely a very nice speedup technique for hyperparameter optimization. The second speedup technique for hyperparameter optimization is to extrapolate learning curves. So let's have a look at typical learning curves of neural networks. Here we have the number of epochs, and here we have the accuracy. And of course, what we want from our learning curves is to go up quickly and then kind of converge to something good. If you use the wrong hyperparameter settings, though, then you can easily get performances like this or just wiggling down here. And that is something that we would just want to get rid of and not actually have to wait all the time until, well, here epoch 300 or so to get this performance value back. And that's what Blackbox Bayesian optimization would do. It would just run for its allotted time or allotted number of epochs and then give us an accuracy that's just horrendous. For cases like that, we would rather want to run this learning curve for a short initial time here and then say, this does not look like it's going to achieve a performance that's as good as the best one that I've seen so far up here. So I will actually just terminate this early and move on and use the time better for evaluating other learning curves. And if you do that, then you can also easily save quite a lot of time, and you can do that actually for all kinds of different methods. So ranging from Gaussian processes to even random search, you can do extrapolations of learning curves like this and then save some time by a predictive termination criterion that was, for example, introduced in this work by Domhan et al. But let's now move to the currently most robust and most effective way of speeding up Blackbox hyperparameter optimization. And that is multi-fidelity optimization. So multi-fidelity optimization, in a nutshell, uses cheap proxies of the expensive Blackbox function in order to speed up the search and to basically rule out poor hyperparameter settings cheaply and then focus on the better hyperparameter settings using the actual expensive Blackbox function. So there is various ways in which we can do this, in which we can define these cheap proxies. So if we have iterative machine learning algorithms, then we can have a cheap proxy by running this algorithm for less time and stopping runs early. If we have k-fold cross-validation, then we can run some configurations only for one or a few folds and reject the poor ones if they do poorly in a few folds. And if we have large data sets, then we can run some configurations on smaller data sets and quickly rule out the bad models based on these subsets of the data. So there's various different ways to define these cheap proxies, and there's many others that we could think of, such as running shallower neural networks, running leaner neural networks that are not as wide, running neural networks with a lower resolution of the images, and so on. And well, here we have an example of how this can be really useful, in this case here for running on smaller data sets. So the example is for optimizing a support vector machine on the MNIST dataset. So on the right here, we have the response surface for the original MNIST dataset, 50,000 data points. Then here we have a quarter of the data. Here we have a 16th of the data. And here we only have a 128th of the data. So this here is only based on 400 data points roughly. And we see qualitatively that the response surface actually looks quite similar in this case and in this case. We can definitely see that this whole area here, that all of these hyperparameter configurations are really poor. Well, they're also really poor here. So we can basically rule out a lot of hyperparameter settings already based on this very cheap function evaluations over here. Why are they so very cheap? Well, they're based on only 400 data points, 128th of the original data, and support vector machines, they actually scale super linearly. So these function evaluations over here actually cost less than 1/10,000th of the cost of a function evaluation over here. So we can do 10,000 function evaluations over here for the cost of one function evaluation over here. So we can invest substantial number of samples in order to figure out what's good for this cheap proxy, and then we'll use these intermediate proxies in order to not risk too much missing the best hyperparameter settings for the most expensive black box function. So we can basically gradually increase the complexity for the good hyperparameter settings. And one way that we can exploit this is by actually using Bayesian optimization and fitting a function that now takes as input not only a configuration, but also the fidelity that we used in order to evaluate this configuration, and then actually have the model pick both the configuration and the fidelity to evaluate this on. And in fact, that's what we've done in this work here, and that actually did achieve 1,000-fold speedups for optimizing support vector machines on MNIST, and that is because, well, there is a strong correlation here across different fidelities, and the runs on the cheapest fidelity, the subset, are much, much, much cheaper than the runs on the highest fidelity. So we can rule out all the bad, well, not all the bad, but most of the bad hyperparameter settings very cheaply. So that's one type of approach, and there's actually various different versions of this. And well, typically these actually are all based on Gaussian processes. And unfortunately, they are fairly brittle. So they have worked in this one case very nicely, and have also worked in other cases, but sometimes they have issues because they need to actually fit this model. They rely on being able to actually build a model that extrapolates over the fidelity. So you want to be able to predict what's going to be good with this fidelity without ever having run it, or with having run like one evaluation there. And well, those predictive models may or may not work well, and that depends on the algorithm and the data set at hand. Now, a cheaper and less brittle approach is actually given by these two algorithms, successive halving and hyperband. In fact, the successive halving algorithm is basically visualized here. It starts by sampling configurations uniformly at random for the lowest fidelity. So basically do random search for this fidelity here. And in fact, all these white X's here are uniform random samples. So this is successive halving. And then the algorithm works by dropping the worst half or worst 2/3, depending on a hyperparameter. In this case here, we drop the worst 2/3 and keep the best third, and then move the best of these to the next fidelity level. Then again, we take the top third, namely these here, move them to the next fidelity, and take the top third, move it to the next fidelity, and we have paid relatively little cost. We only have one evaluation at the top fidelity. We have 3 evaluations at the second most fidelity, and we have quite a lot of evaluations at this lowest fidelity. In this case here, 27. But these are very cheap compared to the ones on the highest fidelity. So this here is an example of successive halving for a budget, a fidelity defined in terms of the dataset size. Here's another example of successive halving with a wall clock time budget. So here we have different learning curves for the different hyperparameters, and basically what successive halving does here, it runs all the different hyperparameter settings for the first budget, throws away the worst ones, so it terminates these here, and extends the other ones, then doubles the budget, goes to here, and drops the worst half, doubles the budget, drops the worst half, and doubles the budget. And only has to pay the full cost, the full wall clock time for these 2 best configurations. Now, one potential issue with successive halving is that learning curves could cross. So you could have the case that the worst configuration that you ruled out here actually in the end does better. That is a hypothetical possibility. And in order to guard against that, the hyperband approach actually wraps around the successive halving approach by starting successive halving with different definitions of the lowest budget. So here is the original successive halving that we saw on the previous slide here. So this has a low, the lowest type of low fidelity. Then you start it again where this is the lowest fidelity, then start it again where this is the lowest fidelity, and then you start it again where this is the lowest fidelity, this here being the most expensive fidelity. So this part here, well, that's actually just random search. And well, because you spend in this case here a quarter of the time just running random search, you have a relatively trivial provable quality that you're not going to be more than 4 times slower than random search. Whereas if you just ran only the successive halving and you have this green case here where this crossing of the learning curves actually leads to the case where you're dropping the best hyperparameter setting early. In this case, you could run this for an infinite amount of time and this would still actually not converge. So in that case, in that sense, the guarantee that you can get from hyperband is actually still meaningful, that, well, you're at least not going to be more than a factor of 4 slower than random search. In practice, however, you very often have strong correlations, and these instantiations of successive halving that start with a pretty aggressive lowest fidelity actually tend to work best. So the unfortunate thing about successive halving and hyperband, however, is that, well, they're purely based on random search. And so they're not at all looking at the history. They're not at all looking at which hyperparameter settings were competitive in the past. And well, that's why we actually combined this with Bayesian optimization in this algorithm called BOHB, BOHB, Bayesian optimization, hyperband. So this is a really simple combination of Bayesian optimization and hyperband. And it basically works by running Bayesian optimization for selecting the configurations and doing so by a variant of TPE, and then using exactly the same hyperband algorithm that we just saw for selecting the budgets for these. So this then recovers the advantages from both Bayesian optimization and hyperband. And hyperband in particular has a lot of advantages, namely it's very scalable, it gives us strong anytime performance due to the hyperband component and the smart scheduling of the budgets. It's very robust and efficient. And well, what the Bayesian optimization part gives us is that it also does well with larger budgets, whereas the successive halving and hyperband algorithm, they get us good anytime performance, but not necessarily the strong performance with larger budgets. And well, this is also BSD licensed and freely available at this URL. So I encourage you to try this out. But of course, here's a disclaimer. I'm a co-author of this paper, so of course I'm biased. Nevertheless, yeah, you could give it a try. And here's some more empirical data to show how Bayesian optimization and hyperband and BOHB relate to each other. So first here we have random search versus TPE, a Bayesian optimization variant. And we see that in the beginning of the search here, there is no speedup whatsoever of Bayesian optimization over random search. And this is not surprising at all, because Bayesian optimization first needs to actually get some samples of the space in order to actually build its model and then figure out which parts of the space are useful and which are not useful. And then in the end, actually it has a better gradient here and gets much faster to the optimum than random search. And so in the end here, we have this 10-fold speedup already, whereas in the beginning we had none. Now, hyperband is the exact opposite. So in the beginning, it has this large speedup because of its multi-fidelity optimization. But in the end, actually the speedup is quite small, partly because it has a lot of overhead by running random search for a substantial part of its runtime, but mostly because, well, there's just no greediness. It's not exploiting the fact that it has seen good configurations and bad configurations and then sample more in the good areas of the space. No, it just keeps on sampling at random, and therefore the speedup actually marginalizes in the end. And then Bayesian optimization then achieves the best of both worlds. So in the beginning, it is actually exactly hyperband, and then at some point when there are enough points evaluated at a fidelity in order to build a model, then it starts to build a model, and well, the BOHB part here starts to deviate from the hyperband part. And in the end, we have this 50-fold speedup over random search. All right, that gets us to the end of this video. And as always, I have some questions for you to think about to activate the material. So I encourage you to pause the video here, and I'll see you in the next video. Thank you.